So our last topic we're covering in this chapter is the ways in which heat can be transferred. So recall, heat is a transfer of energy because a system and its surroundings are at different temperatures. So conduction, there's an electric circuit shown here because we're talking a similar idea that the electrons within the atoms can move from atom to atom to atom within a conductor. It's the valence electrons that are moving, but because atoms share those valence electrons easily in conductors, heat can easily be transferred. So the heat energy can be transferred from a hotter region to a colder region easily on that electron scale. Convection here is when a certain area gets hot, the heating up, again, remember, materials tend to expand when they heat up, which means the density decreases. So the lower density materials, because they're hotter, their density gets smaller, the lower density material rises, and the cooler material that has a higher density will sink. And so we get this lower density going up, higher density going down, and this overall bigger macroscopic motion of the material moving that energy around. Evaporation, when we have the hot material, we end up having the liquid close to a boiling temperature, if not at the boiling temperature. And so some of the energy starts changing phase, and so it's changing from a liquid to a gas. And that is taking energy out of the hotter material and going now into the atmosphere around it. Radiation are what we call electromagnetic waves. Light is a general term we use for that. Typically, when we talk about light, we specifically mean visible light. But there is a whole spectrum. The reddish light that we're seeing here is infrared. Infrared light. There's electromagnetic waves. We can call this infrared radiation as well. So the energy emitted with some form of light. As far as equations are concerned, we're going to talk about equations for conduction and radiation. So the equations, I've just pulled this section from the test notes that talks about heat transfer. So our two equations, this first equation on the left is our equation that describes conduction. Now, dq dt is the rate at which the heat is transferred. So the rate of heat transfer, how fast. So Q, remember, is units of joules because we're talking energy, time, seconds. So our units here are joules per second, which is power. It's a watt. In this equation for conduction, K is called the thermal conductivity, which actually is stated in this paragraph above. It is a constant which is unique to the material. So these values underneath the equations are a variety of K values from a table in the book. The higher the value of K, the faster energy can easily be transferred from some material to another. A is the cross-sectional area. So a window, for example, in our homes, our apartments, our cars, this is my sad picture, our window here, just as an example, when we talk about A, we mean this cross-sectional rectangular area of the window that is the separation between inside and outside. So if I were to draw from the side, my window, I would see just that little thin pane of glass. And then, of course, I just see the house, the walls as well. So we would have inside the house versus outside the house. A, the cross-sectional area, is the area, essentially, that rectangular area of the window that bounds between inside and outside. L is a length. In the case of the window, it would be the thickness of the window. It's the distance the energy has to travel to go between these two locations, inside and outside. In the case of the window, of course. Delta T it's not a final minus initial because we're not talking about 2 moments in time per se. It's a difference in temperature between the two locations where the energy is traveling from and to. Typically, we take the hotter temperature, whichever location is hotter, and subtract the cooler temperature, just so that we get a positive value. So right now, outside is colder than inside my house. So I would take, for delta T, the temperature inside, it's a hotter temperature, minus Tc, the temperature cooler outside. And so just the difference in temperature between the two. These quantities all determine how fast the energy, the heat specifically, this heat energy can transfer from one location to another. So smaller numbers, concrete, 0.8. That's not going to allow heat to transfer super easily. Glass, 0.8 as well. Styrofoam, 0.035. So even smaller, meaning styrofoam will not allow energy to exchange as easily as, say, something like copper. Copper is a very common material for pans, saucepans, that sort of thing. Aluminum. These higher numbers of the thermal conductivity are meaning that the energy easily conducts and transfers the energy, which makes sense as to why copper and aluminum would be good saucepans. If they're good conductors, then they will allow the heat from the stove to conduct nicely into the whatever it is we're trying to heat. A soup, a liquid of just water, whatever it is that we're working with. Now the other equation we have is for radiation. Radiation, again, is electromagnetic waves. It's not the same thing when we're necessarily talking like radiation therapy with cancer treatment or something like that. So it simply means electromagnetic waves. Again, we have a dQ/dt, the rate of the heat transfer. The units are joules per second or watts. E is called the emissivity. This is a number between 0 and 1. It can be 1. Something like a star, like our sun, or a star out in the sky far away would have an emissivity of 1, meaning it's emitting all of the light it possibly can. Now, it's not all visible light per se. It's other forms of electromagnetic waves as well. But that one means it's a perfect emitter. Other materials that are not emitting, maybe like the moon that's just reflecting light, would have an emissivity value that's less than 1. And it just is describing how well it reflects the light. So that is a value that needs to be given to us when we're solving a problem. Sigma in here is a constant. It's a very small number, 5.67 times 10 to the negative 8 watts per meter squared, Kelvin squared. A is the surface area that the light is emitted from. And then T is the temperature. And this temperature must be in Kelvin. And this temperature is to the 4th power. That's something really kind of unusual if we think about all these different equations we've been using. We haven't seen something to the 4th power, per se. This equation is actually used a lot by astronomers, anyone studying in astronomy, because it turns out we have equipment to measure the incoming energy. And so we're able to look at light and get a good idea of the temperature of the stars we're looking at. And by we, I don't mean me, because I'm not an astronomer. The word just came out. Astronomers can look at temperature and relate that to the energy. We can do that as well, just for example, if I go back into my PowerPoints, this picture here on this slide is a satellite image, and it's just looking at the emitted light, the radiation coming from the ocean. Now, the light itself, I mean, if you've ever flown in a plane, you don't see reds and oranges and yellows in the ocean. What is often done is they impose a false color scale, essentially assign a rainbow of colors to the region of temperatures they're looking at, just to put a visual on the picture that makes it a little easier to understand what we're looking at. So here the reds are higher temperatures, the blues are cooler temperatures. So the color we're seeing is directly related to the temperature, so those electromagnetic waves traveling to the detector. Blues, colder temperatures. In here, you can see some of the swirling patterns, which is representing the convection within the ocean as well, where warmer temperatures are moving into the region where there are colder temperatures. So just an example of things we can see and relate the temperature to the energy, the rate at which the energy is moving and transferring. So I'll go through a couple of examples, which will hopefully help, and then we'll be done with the content for this particular semester, which happens to be fall of 2022 in case you watch this in a later semester and it doesn't end up being the end of the semester.